You may have seen what are called off-center rims and wondered what they're all about. In this chapter, I'm going to explain to you the structural benefits of off-center rims, especially for the rear wheel. This is the Velocity A23 rim. We'll call that the standard rim, compared to the Velocity A23 OC rim, OC standing for off-center. The standard rim is good for the front or rear, and the OC is intended for the rear. This is a condensed version of what you can look up on my YouTube channel if you want to see all the details. If you go to my website, seen there, and then go to YouTube and click on the video Velocity A23 off-center rim, you'll see this explained in great detail. Here we see a front and a rear road wheel. If we look at the front wheel, we see that it has equal spoke lengths and will also have equal spoke tension on the two different sides, compared to the rear wheel where we have unequal spoke lengths and unequal spoke tension. The right side of the wheel will have higher tension than the left side. Both of these Velocity rims have the same dimensions, 22.7 millimeters wide and 19.4 millimeters deep. We're going to build two wheels, one with a Shimano 105 hub and a Velocity A23 standard rim, and the other one with another 105 hub and an A23 OC rim. That's the location of the holes in the standard rim. In the A23 rim, the holes are shifted to the left. Now we put some spokes into the wheel. The red lines represent the overlock nut width, which in this case is 130 millimeters. The dashed red lines represent the center of the hub between the lock nuts, which if the hub is 130 millimeters long between the lock nuts, then each of those sections there will be 65 millimeters. Looking first at the diagram on the left, we see we've put a tire on the rim, and if we run that center line all the way up to the top, we see that it goes through the center of the rim and also through the center of the tire, so that the tire is aligned over the center of the hub, and the rim holes are also aligned over the center of the hub. Here we're going to do the same thing. We're going to run our center line all the way up to the top, and we see that the tire is aligned over the center of the hub, but the rim holes are not aligned over the center of the hub. Let's expand this portion of the picture and see what's going on a little bit more clearly. We see that the place where the spokes attach, which is here, is shifted to the left from where the center of the rim is and where the tire attaches. So we have moved those holes about 4 millimeters off the center. Here again is the 65 millimeter distance. That gives us some new dimensions. The 61 millimeters on the left and the 69 millimeters on the right represents the distance from the left and right lock nuts respectively to the place on the hub which is directly under where the spokes attach to the off-center rim. In the completed wheel, if where the spokes attach to the rim is centered over this point on the hub, then the center of the rim will be directly above the center of the hub. These are the exact spoke lengths I need for these wheels: 292.04 millimeters for the drive side of the OC compared to 291.96 for the drive side of the standard, 293.07 for the non-drive side of the OC, and 293.52 for the non-drive side of the standard. The 292.04 on the OC is more than the drive side spokes on the standard, and the 293.07 on the OC is less than the 293.52 on the standard. So I actually get differences as shown here. A difference of the two spoke lengths on the OC of 0.83 millimeters, but 1.56, about twice that, for the differences on the standard. We're going to measure from the outside of the flanges, and using a really good caliper I can come up with these dimensions here, which represent the distances from the outside of the flanges to the line which is directly under where the spokes attach to the holes in the rim. What we have is a right angle there, and another right angle there, and another right angle there, and another right angle there. With a little bit of trigonometry, if we call that angle there theta, the sine of theta is equal to the opposite divided by the hypotenuse. There's my opposite side, and there is my hypotenuse. And I have those dimensions. So the sine of theta is equal to 20.2 divided by 291.96. The sine of theta is equal to 0.069. The arc sine of 0.069 is 3.96 degrees. So my angle there, theta, is 3.96 degrees. In a similar way, I can calculate the other three angles. Now notice the following. The 4.77 degrees that I get on the drive side of the OC is a larger angle than the 3.96 that I got on the drive side of the standard. On the non-drive side, the 6.37 degrees is a smaller angle than the 7.18 I got on the standard rim. When I put some spoke tension on these diagrams, this is what I find. I'm going to put 120 kilograms of force on the drive side spokes of the standard wheel, and on the non-drive side, when I finish the wheel and calculate it, I'll find that I have 66 kilograms of force on the non-drive side when the wheel is dished. In the case of the OC, we'll once again use 120 kilograms of force on the drive side, but the non-drive side comes up to a higher number of 91 kilograms of force. These tension arrows represent force vectors, and they can be resolved into vertical and horizontal components. That's the vertical and that's the horizontal component of the drive side vector. That's the vertical and the horizontal component of the non-drive side vector. When I calculate out the length, that is the magnitude of the horizontal component of those vectors, I come up with 8.28 kilograms of force on both sides. Now let's look at my OC wheel on the right and see what we get for horizontal force vectors in that wheel. My standard wheel on the left with an angle of 3.96 degrees gave me a horizontal tension vector of 8.28 kilograms of force. But on the right, my larger angle here of 4.77 degrees is going to give me a larger horizontal tension vector, in this case 10 kilograms of force. And that is simply because the sine of 4.77 degrees is a larger number than the sine of 3.96 degrees. Here I filled in the diagram and calculated the horizontal vectors on the non-drive side. You can see that in each wheel, the length or magnitude of the horizontal vectors has to be the same. So in the wheel on the left, they're both 8.28 kilograms of force, and the wheel on the right, they're both 10. The length of those horizontal vectors is a measurement of the force necessary to cause the rim to deviate or shift or move from left to right. And what we can see that is in the case of the OC wheel here on the right, we have stronger sideward forces, which will give us more side-to-side stability and less lateral movement of the rim. I can get one other bit of information from these vector diagrams. If I complete this little parallelogram here, the blue line represents the sum of the vertical components of the left and right tension vectors, and that adds up to 185 kilograms of force. In the case of the OC wheel, when I complete that parallelogram, I get 209 kilograms of force. So I'm getting more force, or a stronger wheel, from the OC, even though the drive side tension is the same on both of them. That's happening because the non-drive side spokes of the OC wheel are contributing more to the total strength of the wheel than the non-drive side spokes of the standard. If you look at the YouTube video, you'll see that I supported these wheels horizontally and then put enormous loads on them to cause the rim to deflect, and measure the amount of deflection of one compared to the other. These are the conclusions I reached. I found no mechanical disadvantages of the OC, but some significant mechanical advantages. One is that I have less difference in the drive and non-drive side spoke lengths, and less difference in the drive and non-drive side spoke tension. Less difference in the side-to-side deflection of the rim under side loads, and more total tension with the same drive side tension. Velocity is not the only company that makes rims that are off-center, and you'd find the same advantages with any off-center rim. This is a Cerium SL rim, and I know it's not the greatest shot, but if you look at the holes where the spokes attach, they screw into the rim, of course, you can see they are displaced to one side, and that is the non-drive side of the rim, and that is the drive side. Here are two Mavic Cerium SL rims taped together. There's an old rim and a new rim, and I'm about to transfer all the spokes from the old rim to the new rim because there's a crack in the old rim, actually a half a dozen cracks, and you can see that I have lashed together the two rims with electrical tape. I had to make sure that I got the new rim oriented correctly with respect to the old rim. By the way, I think this is a very good way to transfer the spokes from one rim to another by lashing the two rims together, the old and the new, because this makes sure that all of the spokes in the new rim end up having the same orientation as they had in the previous rim.